Hello, this video covers several of the questions in the homework and a few ideas from the Exam 1A review. So we have a vapor pressure curve, and we're asked some questions regarding volatility, boiling point, and vapor pressure. So let's keep in mind what we're seeing here. You're looking at pressure and temperature are curves in which the liquid gas for that particular substance, for a substance, the liquid is above the line and the gas is below. So if we just take any pressure, I happen to choose 2 megapascals, and as you slowly increase the temperature, we see that the first intersection, which is the first phase change, boiling, for blue happens at 120, and for red at 150. So for our 245 FA at 2 megapascals blue, the boiling point is 120 degrees Celsius. For red, R1336 at 2 megapascal, that's our red curve, the boiling point is 150 degrees Celsius. So that's already a sign, that already gives us a good idea that R245 is the lower boiling point at any pressure. So what does that mean to have a lower boiling point? Well, the first thing that it means is that it's more volatile. Volatility is a measure of the likelihood at any given temperature to put particles in the gas phase. So something like alcohol is volatile as it goes into the gas phase readily at room temperature, while water is not very volatile. It can sit there for a while and still not go into the gas phase. So something that has a lower boiling point is more volatile. At any given temperature, it puts more particles into the gas phase. Okay, but what about vapor pressure? Okay, so vapor pressure is just a quantity that's counting the number of particles in the gas phase. So vapor pressure we're going to see is just the number of particles in the gas phase. You have lots of particles in the gas phase, you have high vapor pressure. You have few particles in the gas phase, you have low vapor pressure. So a low boiling point is more volatile, it puts more particles in the gas phase, and has a high vapor pressure. So using this analysis, we see that the answer is C. High vapor pressure, lower boiling point, more volatile. Okay, so this question is about navigating. Okay, first, at 1 megapascal and 60 degrees Celsius, we are in the liquid region. Right? So liquid region, liquid blue and liquid red. We are to the left of both of the curves. Below both of the curves, we have gas R25, gas R1336, and in between the two curves is the separation region. Right? This will be gaseous blue. We're below the blue line, but liquid red, we are above the red line. Okay, so this is what we call separation. This is the strategy for separation. And we want to know, how do we access this spot by changing temperature or pressure one at a time. All right, so let's take a look at what A says. A says increase the pressure at a constant temperature. That would mean going straight up from our point here. Going straight up would not let us into the separation zone. Increasing the temperature at constant pressure. So moving to the right from this point here. And the answer is yes, that would definitely take us into the zone if we increase temperature, keeping pressure constant. Reduce the temperature at constant pressure, I mean. That would be moving us to the left, and that would not be a good choice. We're not going into. And the final correct answer, which is D, which is lower the pressure at constant temperature, that is correct because that would move us down into the separation zone. So two answers here: increasing the temperature at constant pressure and lowering the pressure at constant temperature. Both of those strategies will take us from 1 megapascal at 60, which is the liquid-liquid interface, and boil blue, which will allow us to separate the two. Okay, this is using representations. If the two refrigerants are held at 1 megapascal and 25 degrees Celsius, which representation is correct? All right, so let's take a look at, where's 125? 125 puts us into the liquid-liquid region. So now what we want to do is identify where is the liquid-liquid region. So that would be item 6. We see two liquids. They're mixed apart. They don't have a fixed, they're not solids and they're not gases. Liquid-liquid. Now we could take a look at these other regions. 5 is not on this graph because it's solid gas. And we don't have any solids in our curve. And then we have 4, which is gaseous red and liquid blue. That is an impossible, right? Not possible, because in the separation region, all we can have is gaseous blue but liquid red. So 3 is possible, and that's in our separation zone, right? The separation zone is number 3. 4 cannot happen. 6, which was our answer, is the liquid-liquid zone. And then we'll see Roman numeral 2 is the gas zone. And then 1 is also wrong because it has solid red and liquid blue, which is not part of our curve for vapor pressure. So remember, our vapor pressure always involves liquid and gas, right? No solids allowed. Okay, this was from a problem. This is where our exam 1A review is. Aside from the questions we just answered, here is a problem for one of our first days in class. And then we just want to analyze it, where we say, okay, here we have the liquid phase. And what do we have? We have liquid water, liquid argon, and liquid oxygen. Well, that's oxygen. And then, so what do we know about the temperature? Well, we know we're below 100, right? I guess we should have said, keep it in Kelvin, 373 Kelvin. And we're below 87 because argon is a liquid. And we're below, so that's oxygen, we're below 90. So we know we're at least below 87 degrees, but we have gaseous nitrogen present. And if we have gaseous nitrogen present, we must be above 77 Kelvin to be in the gas phase. So we're in the gas phase in nitrogen, so we have to be above 77, but below 87, or else argon would not be a liquid. So temperature has to be between 77 and 87. Okay, which of the following graphs represents the energy exchange when air is cooled down and nitrogen condenses? Right, so let's take a look at what we have. So we have a phase change due to condensation, and we have temperature change due to the cooling. So what to keep in mind is condensation is starting at a gas and going to a liquid. That change results in a negative change in delta E. That negative change in delta E is important because that's going to determine our overall graph. As we're cooling, which is a negative delta E, and we're condensing. Right, so with that, going from, all right, so we draw our delta E versus T graph. And remember, we're cooling down, so our initial temperature has to be high. Our starting temperature is high, and we're cooling. So we're going down in temperature. That leads to a negative change. This is cooling, or a phase change, which is condensation, freezing, or deposition, right? Those are all the negative changes in delta E. So we cool the gas. We go through condensation, which is a vertical line at a specific temperature, right? This is the T boiling or T condensation, however you think about it, same temperature. So where that happens, and then we cool the liquid. Sorry, that's supposed to say cool the liquid. So that gives us B, right? It gives us B. A is heating liquid, vaporizing, then heating the gas. So heating the liquid, vaporizing, then heating the gas. That would be A. C starts at T low. So that's wrong. And here we are, T is going down, temperature is going down, but delta E is positive, so that's wrong. So if temperature goes down, delta E must be negative, right? We must start at a higher temperature and go down to a lower temperature. Okay, so with that, good luck. Please come by office hours if you have any questions.